Let's examine the quadratic equation x squared plus 3 equals 0. This is a simple-looking quadratic, but it has an interesting property. To solve this equation, we would need to isolate x squared, which gives us x squared equals negative 3. But can a square ever equal a negative number? Let's visualize this graphically to better understand why this creates a challenge. We can rearrange our equation to y equals x squared plus 3. This gives us a parabola that opens upward with its vertex on the y-axis. Remember, the solutions to our original equation, x squared plus 3 equals 0, would appear as the points where this parabola intersects the x-axis. But notice something important. This horizontal line at y equals 3 represents the minimum value of our parabola. For a parabola of the form y equals x squared plus k, the vertex occurs at x equals 0. So our minimum point is at the coordinates 0, 3. No matter what value of x we choose, the y value can never be less than 3. This creates a fundamental problem for our equation. The parabola never crosses or touches the x-axis because its minimum value is 3, which is greater than 0. Since it never reaches the x-axis, there are no points where y equals 0, which means there are no x values that satisfy our original equation. This geometric visualization confirms what we suspected algebraically. Since x squared must equal negative 3, and no real number squared can ever be negative, the equation x squared plus 3 equals 0 has no real number solutions. To solve quadratic equations like this one, we need to extend our number system beyond the real numbers. This is where complex numbers become necessary. Complex numbers allow for solutions to equations like this by introducing the imaginary unit I, which is defined as the square root of negative 1. With complex numbers, we can express the solutions to x squared plus 3 equals 0 as x equals plus or minus the square root of negative 3, which can be written as plus or minus I times the square root of 3. These are called complex solutions, and they come in conjugate pairs. Here we have a quadratic equation, x squared plus 3 equals 0. This is a simple quadratic equation, but it's going to lead us to an interesting result. To solve for x, we first need to isolate the x squared term on one side of the equation. We can do this by subtracting 3 from both sides, a fundamental algebraic technique that maintains the equality. Whatever operation we perform on one side of the equation, we must perform on the other side as well. This maintains the balance or equality of the expression. Think of it like a scale. If you remove weight from one side, you must remove the same weight from the other side to keep it balanced. By subtracting 3 from both sides, we simplify the left side to just x squared, while the right side becomes negative 3. Let's visualize this balancing concept. Watch as we move the negative 3 terms across the equation. These highlighted negative 3 terms represent the same value being subtracted from both sides of the equation. The equation remains valid because we're applying identical operations to both sides. After simplification, we arrive at x squared equals negative 3. This is a critical point in our solution process. Notice that we've isolated our variable term, but we now have the squared term equal to a negative number. This equation presents us with an interesting mathematical situation. In the real number system, we can't have the square of a number equal to a negative value. Any real number squared always produces a positive result. This means our solution must involve complex numbers, where we use the concept of I, which is defined as the square root of negative 1. The equation x squared equals negative 3 tells us that x must be a value that, when squared, gives negative 3. This is only possible in the complex number system, where our solutions will involve the imaginary unit I. Let's continue with our quadratic equation from the previous scene. X squared equals negative 3. To solve for x, we need to isolate it by taking the square root of both sides. Remember that when we take the square root of both sides of an equation, we're finding the value that, when squared, gives us our original number. On the left side, the square root of x squared simplifies to the absolute value of x. However, Since we're working with a quadratic equation that can have two solutions, one positive and one negative, we need to account for both possibilities using the plus or minus symbol. This gives us two distinct solutions. X equals positive square root of negative 3 and x equals negative square root of negative 3. Let's write these solutions separately to examine them more closely. I'll add a dividing line to make it clear we have two separate solutions to consider. But now we encounter an interesting mathematical challenge. We're trying to find the square root of negative 3. In the real number system, this is problematic because any real number squared always gives a positive result. No real number, when squared, equals negative 3. This raises a fundamental question. How do we interpret the square root of a negative number? If we square any real number, we always get a positive result. So what number, when squared, would give us negative 3? This is where the concept of complex numbers becomes essential. Complex numbers expand our number system beyond the real numbers to allow for solutions to equations like this. They introduce a new unit called I, which is defined as the square root of negative 1. With this new mathematical tool, we can express the square root of any negative number. By using complex numbers, we'll be able to express the square root of negative 3 in terms of the imaginary unit I, giving us proper solutions to our original equation. In our previous work, we arrived at a solution involving the square root of negative 3. But you might be wondering, how can we take the square root of a negative number? To solve this puzzle, mathematicians created a special number called the imaginary unit, represented by the letter I. By definition, I is equal to the square root of negative 1. This might seem strange at first, since we know that any real number squared gives a positive result. This special number I is the foundation of complex numbers, which allow us to find solutions to equations that wouldn't have solutions in just the real number system. Now, let's use this new tool to rewrite our square root of negative 3 in terms of I. Our first step is to rewrite negative 3 as 3 times negative 1. This separates the positive number from the negative sign. This helps us see that we're dealing with the square root of a positive number, 3, multiplied by the square root of negative 1. Using the properties of square roots, we can distribute the square root across the multiplication. This gives us the square root of 3 multiplied by the square root of negative 1. Now let's look back at our definition of I. We defined I as the square root of negative 1. So we can replace the square root of negative 1 with I. This gives us a much cleaner way to express our answer, the square root of 3 times I. This substitution is what allows us to work with square roots of negative numbers. Without I, equations like these would have no solutions in the real number system. Let's return to our original equation and rewrite our solution using the imaginary unit I. Our solution becomes x equals plus or minus the square root of 3 times I. This is the standard form for expressing complex solutions to quadratic equations. Notice how the imaginary unit I helps us express solutions to equations that would be impossible to solve if we were limited to real numbers only. This is why complex numbers are so powerful. These solutions are called complex numbers, consisting of a real part, which in this case is 0, and an imaginary part, which is the square root of 3 times I. Complex numbers expand our number system beyond the real line into a two-dimensional plane. In our previous work with the quadratic equation, we found that our solutions are expressed using the square root of negative 3. Let's finalize these complex solutions into their standard form. When working with complex numbers, mathematicians prefer to write the imaginary unit I before any radicals rather than after. This is just a convention that makes complex expressions easier to read and work with. The plus-minus symbol indicates that we actually have two separate solutions to our quadratic equation. Let's split this expression into these two distinct answers. For our first solution, x equals I times the square root of 3, which we've highlighted in green. This is what we get when we take the positive option from our plus-minus expression. Our second solution, highlighted in red, is x equals negative I times the square root of 3. This comes from taking the negative option in our plus-minus expression. Both solutions contain the imaginary unit I, confirming that our quadratic equation has complex roots rather than real solutions. These two complex solutions fully satisfy our original quadratic equation. When substituted back, both I times square root of 3 and negative I times square root of 3 will make the equation true. This is why quadratic equations always have exactly two solutions, though sometimes they may be complex numbers like we see here. Let's examine the quadratic equation x squared plus 3 equals 0. Unlike typical quadratics, this equation doesn't have any real solutions because the value of x squared can never be negative for real numbers. However, we can find solutions in the complex number system. Our proposed solutions are x equals I root 3 and x equals negative I root 3, where I is the imaginary unit that satisfies I squared equals negative 1. To verify that I root 3 is a solution, we'll substitute it into our original equation. Remember, we need to show that when we plug this value in, the equation becomes true. Now we need to evaluate the square of I root 3. Using the properties of exponents, we can separate this as I squared times root 3 squared. Since I squared equals negative 1 and root 3 squared equals 3, this gives us negative 1 times 3, which equals negative 3. Substituting this value back into our original equation, we get negative 3 plus 3 equals 0, which is true. This confirms that I root 3 is indeed a solution to our equation, even though it's not a real number. Let's follow the same process for our second proposed solution, negative I root 3. We'll substitute this value into the original equation. When we calculate the square of negative I root 3, we get negative I squared times root 3 squared. Interestingly, negative I squared also equals negative 1 because the negative sign gets squared as well, giving us positive 1, and then multiplied by I squared, which is negative 1. So we again get negative 1 times 3, which is negative 3. Substituting back into our equation, we get negative 3 plus 3 equals 0, which is also true. This verifies that negative I root 3 is also a valid solution to our equation. We've now mathematically verified that both I root 3 and negative I root 3 satisfy our original equation x squared plus 3 equals 0. This demonstrates an important concept. Quadratic equations with no real solutions still have complex solutions. To better understand these solutions, let's see where they're located in the complex number system using a geometric representation. This horizontal line represents the real number line, where we normally plot points that correspond to real numbers. Notice that our solutions to x squared plus 3 equals 0 can't be found on this line because they involve the imaginary unit I. To represent complex numbers, we need to add a second dimension, the imaginary axis, which is perpendicular to the real axis. This creates what we call the complex plane, where any complex number can be plotted with its real part along the horizontal axis and its imaginary part along the vertical axis. Our first solution, I root 3, has no real part and an imaginary part of root 3, which is approximately 1.732. So we plot it at 1.732 units up on the imaginary axis. Notice that this point is not on the real number line. Similarly, our second solution, negative I root 3, has no real part and an imaginary part of negative root 3. We plot it at 1.732 units down on the imaginary axis. These two solutions are symmetrically positioned across the real axis, which is a common pattern for complex solutions to quadratic equations with real coefficients. The equation x squared plus 3 equals 0 requires that x squared equals negative 3. Since the square of any real number is always positive or 0, there's no real value of x that can satisfy this equation. That's why we needed to use complex numbers to find our solutions. What we've discovered is that complex numbers allow us to find solutions to equations that would otherwise have no solutions in the real number system. When we square either I root 3 or negative I root 3, we get negative 3, which is exactly what we need to satisfy our original equation x squared plus 3 equals 0.